Wow, ladies and gentlemen, Mr. Esposito, 6th grade science, Ralph Chandler Middle School, and
Mr. Goff, 6th grade math,
Ralph Chandler Middle School. You want to tell them a little bit about what you did today?
I do. You know what I want to do? You know what I want to do?
What do you want to do?
I want to talk a little bit about math. Why can't I talk today? Anyway, yes, you know what I'm going to do is I'm going to show my Math 6 class a little bit of what we're going to do tomorrow. Okay? So those kids who watch tonight can review it, kind of look at it, learn it, so when they come in tomorrow, they're ahead of the game.
Yes.
Okay? And what we're doing in Math 6 is today we talked about the surface area of prisms. Okay, like rectangular prisms, you got to find the area of all the shapes, all the squares and the rectangles that make up that prism. Yep. And then you add them all up. Okay, and we've talked about that before. Or we've talked about that for a couple of days now. And tomorrow we're moving on to surface area of cylinders. Okay, so I have something here that I want to show you. It's the formula for finding the surface area of a cylinder. Okay, so please pay attention. All right, so we have the surface area S equals 2 pi r squared plus 2 pi r h. Well, what in the world is that? Well, when you have a cylinder, okay, so we've got like a little cylinder over here. I'm going to draw it so you guys can see what I'm talking about. It's like a can, all right? Well, a cylinder has a circle on top and a circle on the bottom. Okay, we got to find the area of those circles, okay, because we're finding the surface area of the cylinder. And right here, I'm writing a little r. So that's your radius, right there. How many circles are on a cylinder? 2, like I said, one on top, one on bottom. And then you have a height. The height of the cylinder is from here to here. Okay? So as you can see, we have a radius and a height that we need to find the surface area of this entire shape. And this is the formula we're going to use. So, if I tell you that the radius of this cylinder is, let's just make it easy, 2, and the height of the cylinder is 3, we're going to plug in those numbers into the formula. Okay, so 2 pi r is the area, pi r squared is the area of a circle, and we have 2 circles, so there are 2 of them. That's why it's 2 pi r squared. So right now I'm going to plug in some numbers. 2 pi, what's my r? 2 again. 2 squared. Plus, then we have the 2 pi r h. Okay, that's the height of this cylinder. And we want the distance around it. Okay, so that's 2 pi r, the distance around, the circumference of that circle. So, 2 pi, what's my r? That's 2. And what's my h? 3. So we're multiplying. So, 2 squared. We're going to do this problem now, and of course we use PEMDAS. Parentheses, exponents, blah, blah, blah. There's no parentheses, but there is an exponent. So, 2 squared is what we do first. So that's 2 pi, 2 squared is 4, plus 2 pi, and 2 times 3 is 6. Now over here we have 2 pi 4. 2 times 4 is 8, and we still have our pi, plus 2 times 6 is 12, and we still have our pi, so 12. So we have 8 pi plus 12 pi. That gives us 20 pi. And we're talking about the area, surface area, and let's just call these inches, okay? 2 inches and 3 inches. So 20 pi inches squared is our answer.
Very good.
Now I know I kind of rushed through that, but that's what we're going to be doing tomorrow, okay? Surface area of cylinders. We're also going to talk about the volume of cylinders. All right, so you guys be ready for that. And that's it. Now, Mr. Esposito, I talked for 4 minutes there.
Okay, Mr. Esposito, moms and dads, what do we do today? Well, this is, do you know what that is?
It's the Earth.
That's the Earth. But this is as if we're looking at the Earth, standing on top of it. Woo! This would be, we're sitting at the North Pole. We're living on top of the Earth. This would be the side view. This would be the top view of the Earth. What we went over today, Mom and Dads, we went over the Coriolis effect. Very difficult. It's not an easy concept. It's not something to take lightly because there's a lot of information that builds on this. But if we were to look at this as if we're looking down, can you hold that for me for a minute?
Absolutely.
We're looking down. We're standing right here at the North Pole. Well, guess what? North Pole, that's called the Northern Hemisphere. That's the Northern Hemisphere. And what the Coriolis effect is if you have the wind blowing, Yes, if the Earth wasn't spinning and the wind was blowing, it would appear to be blowing in a straight line. You know what the Coriolis effect is? You know what it is?
I think it's because the Earth spins.
The Earth is spinning.
And so the Coriolis effect is that it doesn't go straight out, it goes...
Yes. So as he turns this and spins it, I am going to spin it to the left.
Okay.
As he spins it to the left, I am going to draw a straight line, but watch what happens to the line. You ready? But turn it slightly. Oh, look at that. It appears... Keep going, keep going, keep going. The wind, what happens to that wind, huh? Look at that.
Oh, man, that's awesome.
Keep going. One more down here. The wind appears to be, what does it appear to be doing?
Spinning!
The wind appears to be curving to the right.
Yeah.
So we are in the northern hemisphere. The wind would appear to be moving to the right, okay? And that's called the Coriolis effect, okay?
That's really cool.
The Earth spinning towards the left, that means the wind will appear to be, it's not necessarily blowing, but it appears to be blowing to the right. So guess what do you think would happen if we were in the northern hemisphere?
It would flip.
It would flip. Now tell me something. If this is the Earth, we're on top, we're here at the pole. Where would the South Pole be?
Underneath?
It would be directly here. Here's the northern hemisphere. Here's the southern hemisphere. We're going to be working on these in class with the first period 1, period 3, and period 4 tomorrow, because today what we did with my period 6 class is we actually did one of these little examples of the Coriolis effect. They made a little disc. They spun it around. One person held it as the other person spun it, and they drew a picture, a diagram of what would happen with the winds. If some students did the northern hemisphere, some people did the southern hemisphere. Then they had to fill this in and tell me which hemisphere it was and which direction did the wind appear to be blowing in. Then what they had to do is they had to turn it around on the back, and they had to write something in the real world, that works like the Coriolis effect. Can you think of anything in the real world that works like the Coriolis effect, Mr.?
Toilet flushing. Is that right?
Toilet flushing. Oh, that is a good example.
Oh.
Here's one right here. Listen to what one of my students wrote. Excellent idea here. If you threw a ball to someone sitting directly across from you on a moving merry-go-round, would the ball go to your friend? By the time the ball got to the opposite side, what would happen? Your friend would have moved, and the ball would have appeared to curve. So you might throw it to somebody, and as they're turning, by the time the ball gets to them, where their seat was, boop, there's another seat there, and somebody else catches it. So that was an excellent example. This might be something that you want to pay attention to at home. I've got all different kinds of examples. If somebody did one of a potter, you know, he's got the clay spinning, and he's pushing down, and when he pushes down on his finger lands somewhere else because it's spinning. So if he's spinning like this, boop, when he stops, his finger is halfway around the vase or the pot. So we'll be doing that tomorrow with first, third, and fourth periods, and hopefully we'll get that done, and that'll be great, and I'll get that into student-led conferences. Moms and Dad, if you have any questions, this is more of a little lesson thing. Goff taught a lesson, and I taught a lesson. Excellent. 2 thumbs up. Mr. Goff, Mr. Esposito, dynamite.
All right.